Good morning. So today I will be discussing about imperfections in crystalline solids. Okay. So before coming to the discussion, one question is written on the board. Okay. And simply I will tell you how to solve this. Okay. And then we will come to our topic. Okay. So in the question, the given data are the density of a lead. Means in this question, density of lead is given, and we know density is rho. Okay, so rho is given here, and the rho is equal to 11.35 gram per centimeter cube. It is equal to 11.35 gram per centimeter cube. And the matter crystallizes with FCC unit cell. So if it is FCC unit cell, then we can say Z will be equal to 4. Okay. Estimate radius of lead atom. Atomic mass of lead is given. Atomic mass of lead is given as 207 gram mole inverse. We have to find the radius of lead atom. Radius of lead atom. Okay. So we have formula for density, and the formula for density is equal to Z into M. Okay, Z into M upon Avogadro number N naught multiplied by A cube. Okay, and it is 10 to the power minus 30 cm cube. Okay, this is the formula for density, we know. Okay, so from here we can say we have to first find out edge length of the FCC unit cell. Okay, then we know relationship between edge length of FCC unit cell and the radius of the atom present. Okay, so at first we have to find out the edge length. Okay, so we have this formula, and from this formula we can say this edge length A cube will be equal to Z into M upon Avogadro number into density into 10 to the power minus 30 centimeter cube. Now put these values. Okay, so from here we can say A cube will be equal to Z, we know it is 4 because it is FCC unit cell, so 4. Okay, into this is atomic mass, and it is given equal to 207 gram mole inverse. Okay, upon this is Avogadro number, and it is equal to 6.023 into 10 to the power 23. Okay, mole inverse into density is given here 11.35 gram per centimeter cube. Okay, into 10 to the power minus 30 centimeter cube. Okay, so from here at first cancel out the units. This is mole inverse. Okay, this is centimeter per cube, this is centimeter cube, this is gram, this is gram. Okay, so cancellation of unit we have done. Okay, now solve this. Okay, so roughly you can say just remove this decimal, so it will be equal to 30. Okay, now it is 207 upon 6023. So if you will multiply this number by 30, okay, then 207 into 30 approximately comes equal to 6 to 3. So it will be 30. Okay, then multiply this 30 with 11.35. okay, 30, just pencil out 10, so it will give you 4 into, it is 100 upon 3 into this much, this will be equal to 5 3 ja 15, 3 3 ja 9, 0, and 3, it will be 4, then it will be 3, 34.05. okay, into, here it is 10 to the power minus 30, here it is 10 to the power 23. okay, so it will be 10 to the power minus 7. Here it will be 10 to the power minus 7. Got it? Okay, now it is 4 upon 34.05. okay, so we can say it will be 100. okay, now cancel out this, it will be equal to 4 8 ja 34, 2.5. okay, so we say it is equal to 100, 4 it will be 7 for 11, means 1 by 8, 5 into 10 to the power 11. okay, so further if you will calculate this value will come equal to 121 into 10 to the power 6 pm cube. okay, this a cube will be equal to this much. Just solve this. okay, further you will get this number. okay, then it will take time if I will be solving this. okay, so simply just divide these. okay, you will get this number. So it is a cube, so it will be equal to cube root of this. okay, 121, we know 5 into 5 into 5 gives 125. it is 121, so take this value as 4.95, because cube of 5 is equal to 125 and this value is 121, so it will be less than cube of 5, so take this value 5.95 approximately I am taking it. okay, into 10 to the power 2, it will be 10 to the power 2 now. okay, and picometer. So this is the value for A. Now we have obtained value for A. okay, edge length came equal to 4.95 into 10 to the power 2 picometer. So from here we can say if it is FCC, then we know relationship between face diagonal. okay, means root 2A is equal to we say it is 4R in case of FCC. okay, if it is FCC, then it will be equal to, okay, this distance is root 2A. we have calculated it many times, so simply it is root 2A is equal to 4R, and from here we have to find out this R. so R will be equal to root 2A upon 4. So put this value, it will be equal to 1.414, okay, into A we have calculated to be 4.95 into 10 to the power 2 divided by 4. Solve this, okay, you will get radius of lead atom. Okay, now we are going to discuss imperfection, okay, imperfections or defects in crystalline solids. So our topic is imperfections in crystalline solids. Okay, these imperfections are also known as defects. So we say imperfections or defects. Imperfections or defects in crystalline solids. Okay. So what happens? The crystalline solids which we were discussing, okay, if it was FCC or BCC, okay, or SCP, all these lattices we were assuming to be perfect, okay, means without any defect. But in practical, okay, no means we say crystalline solids are generally not perfect. Okay, we were assuming this to be perfect, but generally these are not perfect. There are some defect present in them. Okay, or we say there is some imperfection, okay, present in the crystalline solids. Okay, so what are these imperfections? Okay, so simply we say imperfection in solids, crystalline solids, imperfection in crystalline solids are due to the deviation of the lattice from imperfection in crystalline solids are due to the deviation of the lattice, okay, from their ideal lattices. Okay, what is imperfection? Imperfection is in a crystalline solids are due to the deviation, okay, of the lattice from their ideal lattices. Okay, so these imperfections or defects are of two types. Okay, we say these imperfections or defects are of two types. Defects in crystalline solids are of two types. One is called as point defect and other is called as line defect. Got it? There are two types of defects in a crystalline solids. One is point defect and other is line defect. Okay, out of these two we have to study point defect in detail. Okay, and line defect is not in our syllabus. Okay, so I am going to define these two, point defect as well as line defect. So note down the definition of these two. It is point defect and point defect is defined as the deviation of a lattice or we say these defects arises limit the deviation of lattice so point defect is the deviation of lattice from their ideal lattice. Okay, the deviation of lattice from their ideal lattice. Okay, and in this defect uh, the deviation of lattice from their ideal just a minute. Don't write it this manner, write it like point defect arises due to the deviation around a point or atom in a lattice. Okay, write like this. Okay, this definition is simple. Okay, so what is point defect? Point defect arises due to the deviation around a point or atom in a lattice. And come to line defects. So line defects are the defects arise due to the deviation of points in entire row. Okay, so what is line defect? The defect arises due to the deviation of points in entire row. Point defects means, simply I told you what is lattice. When points are arranged in space, okay, and we join these points, then it forms a lattice. We have discussed. Okay, so points, what are points? Points are the particles, the constituent particles. Maybe it is ion, maybe it is atom, maybe it is molecules. Okay, so by its name, point defect means, in this type of defects what happens, certain point means certain atoms, okay, certain atoms gets, we say, gets missing or gets dislocated. Okay, so this defect is around certain point or certain atom. But when it comes to line defect, then in the case of line defect, what happens, the atom, okay, or we say the particle gets missing, okay, or gets dislocated, okay, around a row, around a entire row. Okay, so we will further discuss, okay, about point defects only. We will be discussing only point defects, because line defects is not in our syllabus. So come to point defect, and point defect is classified into Stoichiometric defect. Okay. Second one is non-stoichiometric defect. And third one is impurity defect. So point defects are of three types: stoichiometric defect, non-stoichiometric defect, and impurity defect. Further, this stoichiometric defect is classified into four types. One is vacancy defect, then it is interstitial defect, then it is Schottky defect, and then it is Frankel defect. Got it? Stoichiometric defects are further classified into four types of defect: vacancy defect, interstitial defect, Schottky defect, and Frankel defect. This non-stoichiometric defect is of two types. One is metal excess defect, and other is metal deficiency defect. Got it? So there are two types of imperfections in solid, or two types of defects in solid. One is point defect, other is line defect. Line defect is not in our syllabus. We have to study point defects, and point defects are classified into three types: stoichiometric defect, non-stoichiometric defect, and impurity defect. Okay, then stoichiometric defects are further divided into vacancy defect, interstitial defect, Schottky defect, and Frankel defect. And non-stoichiometric defects are of two types: metal excess defect and metal deficiency defect. Okay, and impurity defect, simply it has no broad classification. Okay, so we will be discussing about stoichiometric defect. Okay, so put heading stoichiometric defect. So it is stoichiometric defects. Okay, first we are going to discuss in case of ionic solids. In case of, say it is first it is non-ionic. Okay, stoichiometric defects in case of non-ionic crystalline solids. Okay, so in case of non-ionic solids, stoichiometric defect shown is of two types. Okay, one is vacancy defect, one is called as vacancy defect, and other is called as interstitial defect. Okay, so we will be discussing vacancy defect and interstitial defect one by one. You have to keep in mind one thing: in case of non-ionic crystalline solids, okay, these means defects are also called as, okay, the defects are also called as intrinsic defect or thermodynamic defect. Okay, these are known as thermodynamic defects because when we increase temperature, okay, then some of the points or some of the atoms, okay, leaves their normal site and it gets misses, okay, creating a hole at their normal sites. So when we increase temperature, this type of defect can be increased. So more oftenly we termed these defects as thermodynamic defects, okay, and also we say it as intrinsic defect, okay, intrinsic defects, okay. Okay, so these defects we say these defects takes place due to vacancy or these defects takes place due to leaving an atom from its normal site, okay. Whenever atom will leave their normal site, normal position, okay, and will be missing out or will take some other place, okay, in that lattice only, then this type of location is called as this type of defect is called as stoichiometric defect in non-ionic crystals, okay. So come to vacancy defect. So vacancy defect is this defect arises when an atom from its normal site leaves their position and gets misses missing, creating a hole at the normal site, at its normal site. Okay, what is the definition? This defect arises when an atom from its normal site leaves their position and gets missing, creating a hole. This one is important. Creating a hole at its normal site. Okay. Just try to understand this. So it is A, B, A, B, A, B. Okay, again it is B, A, B, A, then it is B. It is A, this one is vacant, this one is A, B, B and A. Okay, so it is, figure is two-dimensional representation, two-dimensional representation, two-dimensional representation of a vacancy defect in non-ionic crystalline solids. Okay, so if it is a crystalline solid, okay, whether ionic or non-ionic, if it is crystalline means particles of or constituents of the crystals are arranged in a regular manner. Okay, so it is A, B, A, B, A, B, it is in regular manner. Okay, but look here, it is B, A, B, A and this is missing. Okay, we don't know, means this site is missing. Okay, so if this site is missing, then we will remove this from here. Okay, again it is A, B, A, B, but here again the atom or the particle involved in this lattice arrangement is missing, like this. Okay, so there are two holes, one hole is present here and other hole is present here. Getting it? So come to the definition. This defect arises when an atom from its normal site, okay, this atom from its normal site, okay, this was the site of this atom, okay, and for this atom this is its normal site. Okay, so atoms from normal sites leave their position, okay, and gets missing. Okay, they lived their normal sites and got misses. Okay, got missed. Okay, creating a hole, and in doing this, okay, a hole is created at this position and at this position, okay, at its normal site. So this is called as vacancy defect. So we can discuss some points in this defect, because some atoms are missing, okay, and forming a hole, okay, at their respective normal sites. We say, since atoms are missing from their normal sites, causing hole there, means in this density of the lattice is decreasing. Got it? Means two atoms are missing. Okay, so we say density is decreasing in this case. So in case of vacancy defect, what happens? Density of the lattice decreases. Okay, so in one point we can say due to vacancy defect, due to vacancy defect, density of lattice decreases. Okay, now come to interstitial defect. Interstitial defect. Interstitial defect. So this, we say this defect arises when atoms from their normal sites and gets fitted elsewhere in the lattice. Getting it? What is interstitial defect? It is, we say this defect arises when atoms from their normal sites leave their position and get fitted elsewhere in the lattice. Okay, how? Okay, so let the atoms be A, B, 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 A. Okay, like this. So definition is this defect arises when atoms from their normal sites. Okay, let this atom is leaving its normal position. Okay, and gets fitted elsewhere in the lattice. Okay, and this atom got fitted here. Okay, means it was B, so B got fitted here. Okay, so this defect is known as interstitial defect. Interstitial means the sites, okay, between the space between two particles. Okay, interstitial, okay, means between between the space, okay, of two particles, one atom gets fitted. Interstitial. Okay, so atom leave their natural position, or we say normal sites. So if it will leave its normal site, then a hole will be created there. Okay, and it is not missing after leaving its normal site. This time it is not missing, simply it is fitting elsewhere in the lattice. So as a whole, we say dislocation of atom is taking place. We say here dislocation of atom is taking place. Dislocation of atom is taking place, and that's why these defects are also known as these defects are, or this defect is also known as dislocation defect. Got it? Interstitial defect is also known as dislocation defect. Why? Because dislocation of atom takes place, okay, one atom from its normal sites gets removed, okay, and take place, or between the space, okay, between two particles, means in interstitial site it is getting fitted. That's why this is known as dislocation defect. So in this case, density, okay, density of the lattice do not decreases. In this case, what happens? Density of the lattice do not decreases. Got it? Density do not decreases. Okay. Now come to stoichiometric defects in ionic solids. Stoichiometric defects in ionic solids. So heading is stoichiometric defect in ionic crystalline solids. Okay. So in this case, the defect are of two types. Okay. The defect are of two types. One is called as Schottky defect and other is called as Frankel defect. Okay. One is called as Schottky defect and other is called as Frankel defect. So we will discuss about Schottky defect and then we will discuss Frankel defect. So it is Schottky defect. Schottky is name of a German scientist. Okay, Schottky was a German scientist okay, who observed this defect in ionic crystalline solids in 1930. So Schottky defect is named on scientist Schottky, okay, who was a German scientist who observed first time this defect, okay, in ionic crystalline solids in 1930. So if it is ionic crystalline solids, we know ionic crystalline solids, okay, the constituents of ionic solids are what? Ions. Okay, if it is ionic solid, then ionic solids, okay, are made up of ions, and ionic solids are as a whole neutral. We say ionic solids are, okay, neutral in nature. Get it? means if it is NaCl, so one Na plus is there, one Cl minus is there, so plus minus it gets neutral. Okay, effect of positive charge is neutralized by negative, and effect of negative charge is neutralized by positive charge. Okay, so it is neutral in nature. Okay, we will be discussing this further. Okay, now come to Schottky defect. What is Schottky defect? In ionic crystalline solids, due to in ionic crystalline solids, due to, we say, deviation from ideal lattice, some of the ions gets missing from their natural or normal site. Getting it? In ionic crystalline solids, due to deviation from ideal lattice, okay, ideal lattice arrangement, some of the ions gets missing from their normal sites. Okay, these ions are always present in pair to maintain the electrical neutrality of the ionic compounds. Okay, these ions are always present in pair. What does this mean? Pair means if one cation will be missing, then at the same time, okay, an anion will be missing. Okay, means pair means cation plus anion. Okay, say there are 100 cations and 100 anions. So if two cation will be missing, then at the same time two anion will also be missing. So it will form two pair. Okay, two positive and two negative. That's why it is written these ions are always present in pair, means cation form cation plus anion. Okay, to maintain the electrical neutrality of the ionic compound. I have told you earlier, ionic compounds, okay, are as a whole, if we say, then it is neutral. Number of cation is equal to number of anion. So to maintain electrical neutrality, okay, the missing ions are present in pair, means if one cation will miss, then at the same time one anion will be missing. Okay, now try to understand this. Say it is ionic solid NaCl. So we know if it is NaCl, okay, it is 2D representation of NaCl. So if it is NaCl ionic compound, then it is Na plus, it is Cl minus, Na plus, Cl minus, Na plus, Cl minus. In this way, fill this. Okay. So according to Schottky effect, what happens? A pair of cation and anion, okay, gets missing from their lattice. Okay. So say one Na plus and one Cl minus is missing. Okay. So here it will form a hole, here it will form a hole. Getting it? One cation and one anion is missing to maintain the electrical neutrality of the ionic compound. Okay. So if the ions Na plus and Cl minus will be we say missing, then it will create a hole at their normal site. So here it is a hole, okay, formed. Again here a hole is formed. So we say due to Schottky defect, multiple hole are created. Multiple holes are created in the lattice. Getting it? Multiple holes are created in the lattice. And if you will talk about electrical neutrality, then it will be still electrically neutral. Okay. So the consequence we say is due to Schottky defect, multiple holes are created in the lattice. Now come to conditions required or conditions for Schottky defect. So condition for Schottky defect, first condition is, okay, Schottky defect is shown by Schottky defect is shown by, okay, ionic solids having high coordination number, and second thing is Schottky defect is shown by, okay, we say first is Schottky defect is shown by ionic solids having high coordination number. Getting it? High coordination number means what? A particular ion will be surrounded, okay, a particular ion will be surrounded by more and more we say oppositely charged ion. Okay. So coordination number we know. Okay. Then second point is the size of cation and anion is identical. Okay, we will understand these 2 points in more detail when we will be discussing Frankel defect. Then these 2 points will be more clear to us. Okay, okay, for this time you just note down this and try to remember. Okay, when we will be discussing Frankel defect, then these 2 cases will be crystal clear to you. Okay, so at that time only I will explain these two. Okay, because that time I will be comparing these two and it will be very easy for you to understand these 2 points. Okay, now it is consequence of Frankel defect. Consequence of Frankel defect. Sorry, it is Schottky na. Consequences of Schottky defect. First consequences is due to the formation of hole. Due to the formation of hole in the lattice. In the lattice, the stability of the lattice decreases. Lattice decreases. Okay, second is the lattice energy, the value of the magnitude of lattice energy also decreases. Okay, then if the formation of hole is taking place, okay, means we say density of the lattice will decrease. So third point is density of the liquid, lattice, density of the lattice decreases. Then we say electrical conductivity increases because as electric field is applied, okay, under its influence, ions present occupy the position of hole, okay, forming a new hole at its normal sites. And this process continues and due to this flow of ions is continuous. Okay, flow of ions is continuous, okay, making it more conductive. Getting it? So these are some consequences, okay, of Schottky defect. First consequence is due to formation of hole in the lattice, the stability of the lattice decreases. Second is the magnitude of lattice energy also decreases. Lattice energy I have told you earlier. Then density of the lattice decreases because hole is forming, so density of the lattice will decrease. Then electrical conductivity increases. Okay, because as electric field is applied, under the influence of electric field, ions present will move and occupy, okay, the position of hole, forming a new hole at its normal sites, and this process continues, and due to this flow of ions, okay, due to the flow of ions continues, okay, due to this process continues, sorry, where it is, and this process continues, and due to this flow of ions, okay, and due to this process, okay, flow of ion is continuous, okay, making it more conductive in nature. Okay, means just I am explaining this point. Okay, let it is cation, anion, 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 and cation. So one cation is missing from this place, one anion is missing from in this place. So when you will apply electric field, okay, then what will happen? These cations and anions will start moving, and if it is cation, it will take place of this hole, okay, and if it will take place of this hole, okay, then at its normal site a hole will be created. Okay, suppose this negative means this anion is taking place of this hole, then at its normal sites one hole is forming, okay, and this process will be continuous. Okay, this hole will be occupied by this and making a hole here. Okay, this process will be continuous. Okay, and we can say flow of ions will be continuous, and we can say electrical conductivity will increase. Okay, so thank you. We will be discussing Frankel defect in next lecture.